Hi everyone and welcome to another lecture. Today we want to talk about the Schwarz inequality. If you are familiar with Schwarz inequality, that is in terms of Euclidean space. So the Schwarz inequality in Euclidean space, sorry. So let me write it down properly. Euclidean space version tells you that if you have two vectors, then the modular square of that vectors, that is, these are vectors, so I'm just denoting with an arrow. This is the 3D version, is equal or greater than the dot product thing. This is the Euclidean version that you are familiar with, or you might be, and today we want to see it from a more general point of view, that is in terms of vector spaces. So let's try to do it. So this will be a more general approach, and we will have two vectors. One is alpha, another one is beta. Okay, that seems a bit. Okay, so one of our vectors is alpha, another one is beta, and we are not demanding anything special. That is, we are not saying alpha and beta are orthogonal or orthonormal or their basis. These are just two vectors in a same vector space, two arbitrary vectors, and we want to prove that so it will be the same analogous to this, that is equation 1. This thing over here, we want to prove that this will be analogous to 1. So the first thing is the modulus square of alpha, that is alpha inner producted with itself. Then we'll have beta. This will be equal or greater than the modulus, So this is the thing we want to prove over here, and this is called the Schwarz inequality. And the way to do it is the following. First, we want to write another vector, let's say some gamma vector. Okay, so let me just write the proof. Then you take gamma to be something called, let's say, alpha, and some complex number lambda. This is some complex number, so let me just write it down. Some complex number, and this one is beta. And we know from our axioms that this should always be equal or greater than 0 from our inner product. So let's use this. If we do that, we will have alpha, lambda star, beta. Oops, it should be like this, yeah. And for this part, that is the get part, that will be just alpha, lambda, beta, and this is equal or greater than 0. So now you just take the inner product, alpha alpha, lambda alpha beta, then you take lambda star, beta alpha, and finally you will have this lambda lambda star, which is just lambda modulo squared, and beta beta, which is equal or greater than 0. And in the next line we are going to choose, so let me write it down. We choose lambda to be minus beta by alpha divided by beta inner product with itself. Why have we chosen that? Because this is a very tricky way to do this proof in a very short amount of time, and this relationship that is appearing over here, that is this one, it's always true for any value of lambda. So true for any value of lambda. Okay, so let's choose this thing and let's write it down. Let me choose 12. Okay, this is more appropriate. So if we do that, so put lambda as minus beta by alpha, beta by beta, and here you have alpha beta. Okay, let me give a partition as well. So this is the partition, let's say, so that we don't get confused. Oops. So in the next line you will just write, this is the complex conjugation of this lambda, and there should be a lambda over here, so I'll just write it on the right hand side. Then you have this, oh sorry, there shouldn't be a lambda, my mistake. We are putting the value of lambda as this one. So lambda star is just minus alpha beta and beta beta. Then you have this beta alpha thing, and then finally you have lambda squared, right? So the minus sign is gone now, and because you have a squared, that means you have the same thing twice, or you can think of it as the same thing multiplied with this complex conjugate, because this alpha inner product with beta is in general complex. So that's why we want to write this last term. Let's write it over here. And the minus sign is gone, so first use the value of lambda, that is alpha beta 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 times beta alpha and beta beta, and this is greater than or equal to 0. And now if we do some algebra, that is we multiply with beta beta, that is beta beta, and we multiply. Let's say this is 2, multiply 2 by beta beta. So this is alpha alpha beta beta minus beta alpha alpha beta minus alpha beta beta alpha, and finally we have alpha beta beta alpha. And here I'm sorry, I forgot to write down a beta beta term. It was here. So because of multiplying with beta beta in 2, we will finally have alpha beta beta alpha, which is equal or greater than 0. And you can see that one of this term, okay, why did I write 2 of them? Okay, I wrote the same thing twice, sorry for that. And you can see that one of this term will just kill off this term, so the remaining terms are this over here. These are my remaining terms, and if I just write them in a nice manner, minus, this can be written as alpha modulo beta, right, whole squared, equal or greater than 0. And that's it. This is the proof. So QED. And this inequality is important because it will help us in deriving the uncertainty principle. And this is analogous to the vector 3D Euclidean space version that we saw. I mean, we talked about at the very beginning, and this is called the Schwarz inequality. So this is how we can prove the Schwarz theorem. Schwarz inequality. And there is another inequality called triangle inequality. Let's say if you have two vectors v and w again, then the triangle inequality says that the modulus of v plus w is equal or less than modulus of v and modulus of w. And we're not going to prove it because this is geometrically very intuitive. And the reason we discuss these inequalities, especially the Schwarz inequality, that is, let me just mark it again with the blue color, because it will help us to get the uncertainty principle. So that's the reason we discussed these inequalities today, and this will be it for today, and thank you.